All right, let's talk about one of the most fundamental things in all of computer science. How do you get a brilliant idea out of your head and into a machine? It's this whole journey from a simple human thought to an instruction a computer can actually follow. We're going to break that entire process down right now.
So this is really the core of it all, right? You've got this great idea, but computers, well, they're powerful, but they are incredibly literal. They need every single step spelled out perfectly. They don't get nuance. So how do we bridge that massive gap between our abstract, kind of fuzzy human ideas and the super concrete, logical world of a machine?
Well, it turns out there isn't just one single path to get there. We're going to walk through 4 key ways to make this translation happen. We'll start with plain English, then move to drawing it out with flowcharts, then drafting a blueprint with something called pseudocode, and finally, writing the actual programming language. Each step gets us closer and closer to something the computer can finally understand.
Okay, so let's start with the tool we all use every day, our own language, just plain old English. And to make this concrete, we're going to use a simple little algorithm for translating words into Pig Latin. At this stage, you just describe the rules, exactly like you were explaining the game to a friend. But right away, we hit a snag. The upside of natural language is obvious. Everybody gets it. It's fantastic for just kicking ideas around with other people. But the downside? It's way too vague for a computer. Phrases like, move the first letter to the end, what does that mean exactly? That ambiguity is a total deal breaker for a machine. We need more structure.
So, how do we add that structure? Let's try drawing it. This brings us to our first formal method, the flowchart. This is a huge step because we're moving away from just talking about the algorithm and toward actually visualizing how it works step by step.
Basically, a flowchart gives our logic a physical shape. Every box is an action, and the arrows connecting them show the exact path the process takes. It's like creating a map for our idea. Here's what a super basic one looks like. See that? It's just a straight line. Each one of those rectangles is a specific action, one after the other. It's simple, it's direct, and most importantly, there's no ambiguity.
But what happens when our algorithm needs to make a choice? This is where it gets interesting. We introduce this diamond shape. That diamond asks a question. In this case, is the first letter a vowel? And notice how the arrows now create 2 different paths, a yes path and a no path. This is called selection, and it suddenly makes our algorithm a whole lot smarter.
And now for the final piece of the puzzle. What if we want to translate a whole sentence, not just one word? For that, we need a loop, or what's called iteration. See that arrow that goes back up? That tells the process to run through the whole sequence again for the next word in the sentence. And just like that, we have a complete visual map of our entire algorithm.
And this is so important. Making a flowchart isn't just an arts and crafts project. It forces you to think really hard about the details. Does this step really come after that one? What happens in this case versus that case? It makes your logic solid and helps you spot problems long before you write a single line of code. Okay, so we've got our visual map. Now let's build on that. We're going to move from the drawing to a text-based blueprint that acts as the perfect bridge between our flowchart and the final program. This is what we call pseudocode. The best way to think about pseudocode is just fake code. It uses words you'd see in programming like for each or if else, but you don't have to stress about getting the syntax perfect, like where to put a semicolon or a bracket. It's a tool for the programmer's brain, not for the computer.
And here's our Pig Latin algorithm written out in pseudocode. Look at how it matches our flowchart. The for each part, that's the loop we drew. The if-else part, that's our diamond decision block, just written out. It reads a bit like structured English, but it perfectly captures the logic from our diagram.
So you might be asking, why bother with this extra step? Well, it's huge because it lets a programmer plan out the entire logic using concepts they already know without getting stuck on the tiny, picky rules of a specific language. It becomes this universal blueprint that any developer in the world can understand, no matter if they code in Python or Java or anything else. Which of course brings us to the grand finale. It's time to take that carefully designed blueprint and translate it into a real, actual programming language that a computer can finally run.
And there it is, the final code, written here in JavaScript. But look closely. It's almost a direct, line-by-line translation of our pseudocode. Our for each idea is now a proper for loop. Our if-else is still an if-else statement. All that planning we did with the flowchart and the pseudocode made this final step just a logical translation. This is our idea, finally made real. So let's step back. What's the big takeaway here? We've just seen how one single simple idea, translating to Pig Latin, can be expressed in all these different forms, and each form serves a really important purpose.
Think about it. We started with a casual, conversational idea. Then we gave it structure by drawing a visual map. From that map, we drafted a detailed language-independent blueprint, and only then did we build the final, working program. Each step refines the idea, adding more and more precision and stripping away all the ambiguity. And that blueprint, the pseudocode, it is incredibly powerful because that one blueprint, that one set of logical steps can be translated into, get this, more than 700 different programming languages.
And if you don't believe me, go check out a site called rosettacode.org. It's this amazing wiki that is just packed with examples of algorithms, all translated into hundreds and hundreds of languages. It is a mind-blowing example of how the underlying logic, the algorithm itself, is the one true constant. The language is just the final detail.
Which kind of leaves us with a final big idea to think about. The syntax, the specific words, the brackets, all that stuff changes from language to language, but the logic, the sequence of steps, the decisions, that stays the same. So if one single algorithm can be described, mapped, blueprinted, and built in hundreds of different ways, maybe the algorithm is something more fundamental, something closer to a universal truth than any single language we use to write it down.